My name is Gabriela Cornejo, and this is my video lab report for Lab 3, the magnetic field of a bar magnet. The purpose of this lab was to determine the distance dependence of a magnetic field due to a small bar magnet for both on-axis and off-axis magnetic fields. The other purpose of this lab is to give us a better understanding of magnetic fields through the use of a smartphone app to measure the values ourselves. The use of our own phone to do the measurements will provide a better visual frame of reference for us to reinforce the ideas learned throughout lecture. The general results of this lab were that the distance dependence was calculated to be approximately -3.0183 meters, and the magnetic moment of the magnet calculated during this lab was found to be 1.83 amperes times meters squared. These values were calculated using the experimental data and the equation for the slope of the line of the average magnetic fields. The fundamental physics principles used in this lab are the Biot-Savart law for calculating magnetic fields with the magnetic dipole moment mu, where the magnetic field is equal to the equation shown here. The general idea of magnetic fields and how they function is also important in this lab because we have to compensate for the Earth's magnetic north in this experiment. Otherwise, the results of the magnetic field of just the bar magnet would not be accurate. Shown here is the experimental data that I collected using the smartphone app. On the left-hand side are tables with the on-axis magnetic field measurements. The bottom table shows the off-axis magnetic field measurements, and the graph shown is a line graph of the averages of the magnetic fields. Using the slope of the line equation, y equals -3.0183x minus 14.819, we see that the distance dependence n is equal to -3.0183 meters. We can solve for the magnetic dipole moment mu by using -14.819 as the value of natural log of b. Rearranging the magnetic field equation with our experimental value of the natural log of b, we get that e to the natural log of b is equal to the constant mu naught over 4 pi times 2 mu over the distance cubed. E to the natural log of b gives us just b, the value of the magnetic field, and in this case r equals 1. Thus, plugging in the values gives us a value of 1.83 amperes meters squared for mu. Some of the observations I made while conducting the experiment include that when the magnetometer is far away from the magnet, it measures a near zero magnetic field in the x direction. This is because we have to compensate for magnetic north. As the magnetometer moves closer to the magnet, the measured x component of the magnetic field increases. And for the magnetic field in the y direction, for the perpendicular measurement, we have to compensate for Earth's field by subtracting the by Earth value from the measured y value. To create my computational model using Python, I first inputted the value for the constant mu naught over 4 pi, and then created a visualization of the magnet at the origin. I then plugged in my calculated value for mu and created a function to calculate magnetic fields. I then came up with a scale in order to actually show my magnetic field arrows on the computational model and came up with a distance to place the arrows from the origin. I then created my observation locations for the magnetic field arrows, where there's 2 on-axis arrows and 4 perpendicular ones. I then calculated an actual value for the magnetic field arrows using the magnetic field function I created earlier and my observation locations. I ended up multiplying this value by the B scale in order to get the arrows to actually show up on the screen. This final portion of my code is to create the magnetic field arrow for an observation location about 45 degrees off axis. I did this using an experimental value and my magnetic field function. This is what my computational model ended up looking like. The purple arrows are the on-axis magnetic field, the blue arrows are the perpendicular magnetic fields, and the green arrow is the 45-degree magnetic field. And the calculated magnetic field values are shown at the bottom. If we had not oriented the experiment to compensate for magnetic north, then the results would have been completely different. By compensating for magnetic north, we ensure that the x component of the magnetic field starts at 0 teslas so that the only value being measured is the magnetic field from the bar magnet. If we didn't do this, then the measurement would change depending on the value left in the x direction because it wouldn't start at 0. If we were to stick 2 identical magnets together end to end and run the experiment again, then the measurements would differ by being greater than that of before, but it wouldn't necessarily be twice as strong, just greater. In conclusion, the results of this lab were that the distance dependence was calculated to be negative 3.0183 meters, and the value of the magnetic dipole moment mu was calculated to be 1.83 amperes meter squared. These values were found using knowledge on magnetic fields and the Biot-Savart law and its applications that we have learned throughout lecture.